Uh, Hello, everyone. Today, I would like to share my paper named StructSim, Querying Structure Node Similarity at Billion Scale. Here is the outline of my today's presentation. Let's start at the introduction part. In this paper, we would like to compute the row similarity between two nodes. And row similarity is actually a kind of structure node similarity metric and has an additional property of automorphism confirmation that the similarity between two nodes U and V is 1 if there is an automorphism from U to V. Generally, your row similarity is used to quantify the similarity between two nodes in terms of their rows. Examples of rows are a scholar's academic rank in the academia, enzymes in the PPI network, and authorities in the web graph, to just name a few. So row similarity has extensive applications. It can facilitate row discovery in social science, and it can predict the function of an unknown protein in bioinformatics. And also it can help classify or cluster nodes in the graphs, and it can also help detect anomalous nodes. There are two state-of-the-art works on the row similarity. The first one is RoleSim. Actually, RoleSim is the first one to compute the row similarity. And it formally defines the properties of a row similarity metric should satisfy. Okay, RoleSim is based on the iterative computation framework as SimRank. You can see this is the computation framework. The difference is RoleSim involves a maximum matching part between in the computation. However, RoleSim faces with severe performance bottlenecks. First, it cannot scale to large railroad graphs, as it faces with high time complexity and high space complexity. Note that the space complexity is O(n) squared, as RoleSim must store the similarity values for all node pairs. Moreover, RoleSim is constrained to the all-pair computation, which means one has to pay the all-pair cost even when only interested in the single pair or single source queries. The second work is NAD. NAD is proposed to compute structure node similarity based on the k-adjacent trees. Note that the k-adjacent tree is a kind of breadth first search tree of the node, but it may involve the already visited nodes in multiple levels. For example, in Figure 1, in the true adjacent tree of node A, B prime are actually both node B, and C prime are actually both node C. Okay, with the k-adjacent tree, the net distance between two nodes is the summation of the level-wise tree added distance of the respective k-adjacent trees. NAD has severe performance bottlenecks as well, and it cannot scale to large railroad graphs. Specifically, NAD needs OK tau square time to query one single pair, where tau is the average number of nodes in each level of the k-adjacent trees. However, tau cannot be bounded by A. As I said, some already visited nodes may be involved in multiple levels. This motivates us to propose an algorithm to resolve the scalability issues of existing algorithms. Okay, before stating our solution, I will show you the problem definition. The similarity metric, the role similarity metric has 5 properties, namely range, symmetry, automorphism confirmation, transitive similarity, and triangle inequality. A similarity mirror is an admissible role similarity metric if it satisfies all the 5 properties. So in this paper, we studied the problem of computing the admissible role similarity metric for any pair of nodes on an undirected and unlabeled simple graph. Okay, so in order to compute the role similarity, we propose the StructSim framework in this paper, as shown in algorithm 1. The StructSim framework bases the role similarity computation on the hierarchical k-neighborhood subgraphs, where a node's k-neighborhood subgraph is an induced subgraph that contains all its neighbors within k-hop. Note, compared to net, our k-neighborhood subgraph will only include each node once, so its size is bounded by n, by the node size. Okay, StructSim computes the similarity of the node pair, while the weighted average of level-wise similarities between their respective k-neighborhood subgraph from line 2 to line 12. Okay, in particular, we deploy 2 operations, namely matching and delta, to dynamically update the similarity value level by level. Compared to the, compared to the iterative framework at RoleSim, our StructSim framework can better support ad hoc queries. Okay, let's see how to design the matching and delta operations. Our first attempt is maximum matching, and specifically we compute the matching in line 10 to maximize the delta value in line 11 in algorithm 1. As for computing the delta operation, we assign the score as the initial degree ratio for each node pair. For example, in figure 2, we show you node U and V and its neighborhoods. You can see x1, x2, x3 as U's neighbors, y1, y2, y3, y4 as V's neighbors. And each grid records the similarity value between each node pair. And the maximum matching process between U's and V's neighbors finally finds the matching x1 matches with y3, x2, y1, x3, y2. And the delta value is accordingly computed as 0.45. We can prove that StructSim with the maximum matching is an admissible role similarity metric, and the time complexity of querying one single pair for StructSim max is OND plus NI square log NI, where ND comes from online constructing the k-neighborhood subgraphs, and NI is the average size of IHOP neighbors. And the space complexity is ND, OND plus NI square. Okay, compared to ND, StructSim max is more efficient. Compared to net, StructSim max is more efficient to compute as NI is bounded by N, and compared to RoleSim, StructSim max better supports ad hoc queries and is more space efficient. However, StructSim max is not suitable for computing the all-pair queries, so we designed the BinCount matching to accelerate the computation. The BinCount matching is based on the observation that the maximum matching tends to match nodes with close degrees. So we devise the BinCount matching as we group the IHOP neighbors into several bins according to the log value of the degrees. And then we only compute the matching between the nodes in the same bin. For example, in the previous example, we divide the nodes in used neighbors and with neighbors into 4 bins. And then, and accordingly, we only match the nodes in the same bin. So finally, with the BinCount matching, x2 will match with y1, x3 will match with y2, and x1 cannot match with y3 anymore, as it actually contributes little to the final score. We can also prove that StructSim with the BinCount matching is an admissible role similarity metric. Okay, the time complexity of the StructSim based on the BinCount matching querying one single pair is O and D plus K log D, where D is maximum node degree, and the space complexity is this one. So you can see StructSim with the BinCount matching is very efficient to compute. Let's see the performance study. We first studied the effectiveness of our StructSim based on the real-world air traffic networks. We compute the precision on finding top K most similar nodes, and here is the results. Okay, we can see that StructSim variance performed similarly in all test cases compared to RoleSim and NAND. And then we studied the efficiency of StructSim on large networks, in which we use one data set with 1 billion edges. Here is the running time. We do the experiments on single pair query and also on the all pair computation. We can observe that StructSim variance are significantly faster than the baseline algorithms, and the StructSim BC is the only one that can query on graphs with billions of edges. Okay, in this paper, we present a new framework, namely StructSim, to compute node role similarity. We proposed 2 different matching methods for the StructSim framework, which not only ensure the admissibility, but also are efficient to compute. StructSim is the only one that can query role similarity on billion scale graphs. That's all, thank you.